6.4 Day 2 still works with graphing sine and cosine functions and will still have a and b that will stretch and compress vertically and horizontally. Now we'll do some translating left and right and up and down by changing values within our equation. Again, like I said, we're still going to have sine and cosine. And we'll look at amplitude and period of the function with the a and the b value. The amplitude is that absolute value of a, and that's the vertical stretch or compress, so nothing changes there. The period of the function is that b value, and the b value will stretch or compress in the opposite direction horizontally. And we know that we use that b value to make our new start and finish. But now we add on this vertical and horizontal translation. A vertical translation is going to be anything that's added or subtracted after the trig function. In our two equations, the d value is going to represent the vertical translation. And what that will do is just shift everything up or down. And it'll do that in the same direction. So if it's positive, it'll move it up. If it's negative, it'll move it down. That's its direction. There we go. So that will affect your outputs. Therefore, to adjust the outputs, your y values are now going to first be multiplied by a, and then we add whatever d is to that amount. And that will give us our new output table. So we have to affect both adjust both outputs and inputs. The horizontal translation is again what's going to be the tricky one because it deals with the b value. Or the x value. Wow, I'm thinking this through, you guys, I promise. If we look at the inside, there's a parenthesis that's being multiplied, or x is being multiplied by b, but then also there's a minus c in there. If you have anything in the parentheses being added or subtracted to x, that's going to give you a horizontal translation. And what that will do is it will shift left or right, but in the opposite direction. So if it's adding, you'd move it to the left, and if it's subtracting, you'd move it to the right. It's kind of crazy. So we'll say in the opposite the direction. Okay. To figure out your inputs, this is going to be the new x values. We take our bx minus c. So if there's anything in parentheses with an x, we set that whole thing equal to 0. Instead of just the bx part, we have to do the whole thing. And then we set the other part equal, not plus, it still says minus, whatever the inside of the parenthesis is. Bx minus c, we set it equal to 2 pi. This will be our new start. And then this will be our new finish. I can't even write what I'm saying, you guys. This is how great it's going to be. This is our new finish. So what we'll do in the video is we'll just try the first two examples together. One where our input tables stay exact with pi, and then one where we have to approximate. As we look at our equations, what we want to try to decipher is if we have a, b, c, and or d. Depending on what variables we have, we do some or all of the translations. It says sketch the following translation. Y equals 3 sine x plus 2. I notice right away we have an a value out in front. So a equals 3. Because of that, we know the amplitude is absolute value of 3. And since that's greater than 1, our graph is going to stretch vertically. That's the same as what we did in day 1. Nothing too crazy there. We're good to go. Notice there isn't a number in front of x itself, so the b value technically would default to 1. There's no change in the b value or the period of the function. That's good. That's easy to work with then. But now, you guys, we have this plus 2, and we've got to figure out, is that c or is that d? So if we think about the rule with the parentheses, the plus 2 isn't in parentheses with x. That means it's going to be the d value. So d equals plus 2. And what that means is everything is going to translate or move up 2 units. Now the A and the D value both affect your outputs. So these both are output related. The nice thing for this first graph is that when we graph our parent function, we're going to use those same input values in our new graph. We'll just change up where our output values go. All right, so now we kind of start off business as usual. We're going to create our table for sine. And I know some kids ask, do we have to write this out every time? Yes, it's not the end of the world. I have faith in you. I believe you can do this. So I would like you to write all of this out. And then we use this as our template for our new graph. Now remember, sine starts with 0, goes up to 1, 0, -1, and 0. Go ahead and pause the video, you guys. Plot this graph from edge to edge. Press play, and we'll continue on with our new graph. And hopefully your graph looks something like mine. Remember to sketch your graph from edge to edge. Now for our new graph. Remember, our inputs are going to stay the same, so this is pretty helpful for us. We're going to have 0, pi over 2, pi, 3 pi over 2, and 2 pi. To get our, dropped my pen. To get our outputs, we're going to multiply our y value times a, so that'll be 3y, and then we add 2 to that. So this takes a little bit more work than last time, but we use our same our outputs as we did from our parent function. So at 0, 3 times 0 is still 0, plus 2 moves it up 2 units. At 1, 3 times 1 is 3, plus 2 is 5. At 0, we go back to 2. At -1, 3 times -1 is -3, plus 2 would equal -1. And then we go back to 2. Those numbers look pretty crazy. It doesn't look like they match up at all. Let's take a look on our graph and see what this is going to do. Remember, we said it's going to stretch vertically and move up 2 units. At 0, I go up to 2. At pi over 2, we go all the way up to 5. And then at pi, we go back to 0. At 3 pi over 2, we drop down to -1. And at 2 pi, we go back up to 2. So if we connect just those 5 points, up, down, and up, it looks like, yeah, we did stretch it, didn't we? It's taller than it was before, and everything moved up 2 units. Now let's continue the path from edge to edge. Pause the video, do that, press play, and we'll go to the next example. When you're done, hopefully your graph looks something like this one. Take a look at this last equation. Y equals 1/2 times cosine pi over 4x minus 3. Wow, there's a lot happening here. Let's go ahead and start from left to right. We know that the number in front of the trig term is our a value. In this case, a equals 1/2. Now the amplitude is always absolute value. Just get in that habit. Even though positive 1/2 is going to stay positive 1/2, because that's less than 1, this is going to compress vertically. And then we have b, oh goodness, is pi over 4. So if we think about what kind of number pi over 4 is, 3.14 divided by 4 is approximately 0.8. And that's also technically less than 1. But instead of compressing vertically, this graph is going to horizontally, this graph is going to stretch horizontally because it always does the opposite. And we'll show why in our table. And then we have that -3. And again, you guys, notice it isn't in parentheses. It has to be in parentheses in order to change x. So it's not c again, it's going to be d. And this time it equals -3. Because of that, the graph is going to move down or translate down 3 units. All right, so we know A and D affect our outputs, those two. And B is going to change our table. So let's figure out our new input values. We take pi over 4 times x and set it equal to 0. To get x by itself, we'd have to multiply by 4 over pi. And that really doesn't do a whole lot for us because 0 divided by or times anything is 0. So that's our new start value. Let's see where we end. If we set pi over 4 times x equal to 2 pi, and we multiply by the reciprocal, the pi's cancel, the 4's cancel. On the right, the pi's cancel, and 2 times 4 is 8. That's going to be our new finish. Seems kind of weird. But notice the graph I gave you doesn't have divisions of pi. It's an integer graph. That means we have to approximate our parent function and our table. All right, we'll get to that in a second. Let's plot our parent function. Y equals cosine x. So we're going to remember approximate our input values, and we did that in day 1. For our table then, we have x and y. We know we start at 0. Remember, we said pi over 2 is approximately 1.6. Pi is approximately 3.1. 3 pi over 2, it's about 4.7. And 2 pi is about 6.3. Cosine's outputs are 1, 0, -1, 0, and 1. Sketch the graph from edge to edge, and then we'll move on to our new graph. Hopefully your graph looks similar to the one that I've shown on the grid. For our new graph, all right, we have a start and finish for x, and we're going to go from 0 to 8. And we have to divide that up somehow in the middle. Halfway between 0 and 8 would be 4. I guess that wasn't so bad. Halfway between 0 and 4 is 2. How about halfway between 4 and 8? That would give us 6. So our new table, we can handle that. For our outputs though, remember we have an a value of 1/2, so we have to multiply our outputs by 1/2 first and then subtract 3. Let's see what we can do with that. Remember our first output is 1. If we multiply 1 by 1/2, it's just 1/2. 1/2 minus 3 is -2.5. And then we go to 0. 1/2 times 0 stays 0. Minus 3 would be -3. Then we go to -1. 1/2 times -1 is -1/2. Minus 3 would be -3.5. So we're really not fluctuating too much with our outputs. Back to 0, 1/2 times 0 minus 3 would go back to -3. And then +1, 1/2 times 1 minus 3 would be back up to -2.5. So we should have some kind of curve to this. Let's plot these points and see what happens. If you plot the points and connect them, you see somewhat of a curve for cosine, but not quite as dramatic as we've seen with some equations in the past. That 1/2 really compressed our shape vertically. Now the test, can you move it left and right in both directions? See if you can plot by 2's and going up and down just 1/2, and then press play, and we'll call this video done. This is about as good as I can get with our cosine function. Notice it is stretched a little bit. It doesn't quite curve at the same times the parent function did. So it's moved down definitely by 3 units. It's definitely a lot lower than the original. And that's our graph with a change in A, B, and D. Tomorrow we'll do a couple of more examples.